Hello, am I audible? Hello, hello, am I audible? Hello. Hello, let's wait for a minute so I'll see if everyone else wants to join, then we can start. So in this session, we will again see a few questions from the past week that are related to calculations of output resistance and short circuit transconductors, and we will see how we can calculate the gain in those circuits. Let's start by 6.5. Maybe there is someone who will join in these moments. think we should start. Okay, do you have any questions from classroom or any general queries, questions?
First of all, Teachers Day.
Hello, hi Vinod. Your voice was not audible. If you have anything to say, you can just mention in the chat. If no, then I think we waited for some time. Let's get started. Okay, so we need to solve this question. And what is our goal? Goal is to calculate V out by V in. That is gain. Small single gain. Okay, we need to calculate this. So there are multiple approaches. Let's first study how we can calculate the gain. One way is to calculate, uh, we need to calculate the output by V in, and we have here as an output node. What we can do is, we know gain is GM of the transistor, that is here GM2, or not GM2, GM effective multiplied by R out, that is total out. And your total R out will be this R out 1 here in this direction, and R out 2 in this direction, and your R out will be R out 1 parallel R out 2, right? So let's first see how we can calculate the resistance in this portion. Okay, so these are two transistors, PMOS, and we need to calculate this resistance. What are we looking into here? This is source, right? And this will be drain for this transistor. This is M3, this is M4. Similarly, this is source and this is drain for this transistor. We are looking into calculation of R out is looking into drain. Okay, let's just start the calculation. Small signal model. We will derive this relation and then I will just directly tell you how you can remember the formula. Uh, but, but we need to see how we arrive at these formulas. Small signal equivalent circuit. So we have two PMOS. Let me just say this is gate, it is grounded. And then I have current from source to drain. That will be GM4 VSG, and this will be RDS4, and this will be grounded again. And then we have in the bottom another PMOS. that is RDS3. This will be GM3 VSG. Okay, and here the gate is again grounded. So we can see here, this is source, this is gate. So this will be 0, right? This will be open circuit. So we can simplify it further. It will be simple RDS4 here. This will be ground. Is it clear? Now we need to find this resistance. Let's call it R of 1. We need to find this resistance. We will attach a S source Vx and a current of Ix. Is this clear still now? You can unmute your mic anytime if you have any confusions. Okay, so now we have this. Next is simple KCL. Let's call it as node X. KCL as node X. We will have current Ix, incoming current, plus GM3 VSG is equivalent to, let's say, the current in this direction. This will be Vx. Let's call it as VM. This is drain. Let's call it anything. Let's say this is VD4. Vx minus VD4 divided by RDS3. RDS. Okay, correct. Now, since Ix is coming into this branch and it gets distributed among these two branches, one branch is this one. So the total current leaving here should be Ix as well, right? So okay, so now at this node, calculating here, let's call it as x1, let's say this is x2. So potential, or directly, I don't need to call it x2. Potential, can you tell me what will be the potential VD4? It will be simply Ix multiplied by RDS2, right? So this current Ix is fluid. Okay, let me just quickly repeat what we are doing because he joined late. So we have the circuit, we need to calculate gain, and we will see two ways. One in which we will just directly write the formula, and one in which we do the analysis of the whole circuit. Okay,
Sir,
so
sir,
yes,
sir, could you please through formula? Could you please tell it again in reserve manner, sir?
what
It
what
is more
what I
in
didn't get.
reserve manner. You will say no, sir, through GM and R out.
Uh-huh.
Could you please say it again, sir? Because it is very. I mean, I'm getting the points directly, sir. While you are saying,
What are you getting? You're not getting, or you're getting the answers.
yeah, or I'm getting, sir. That was I'm trying to say. Could you
Okay.
please saying GM and R out manners,
Yeah, yeah,
reserve
yeah.
manner?
I didn't get again what you. Can you just write it in the chat? I'll,
No, no, sir. In previously you said no, sir. Through GM and R out, through Razavi manner, you will explain, sir. Razavi. See,
I
you will first will.
okay. Is this method in Razavi? You are telling me that?
Yes, sir. Yes, sir. First we'll find out R out, and we'll multiply with the GM, no, sir.
Yes.
As you said in the earlier previous case. Could
Hmm.
you repeat again to this problem also, sir?
Yeah, yeah. I will. I will repeat definitely. We will have both the methods in this as well.
Yes, sir.
So first we will just solve the whole circuit. Then directly we will use the formulas to solve the question. Okay.
Yes, sir.
So in this question, what we need to do is we need to find V out by V in. First step is we need to calculate total R out resistance. But here we are first concerned about the part this one. First, we will calculate what is the resistance of this part. For that, we made equivalent circuit for transistor M4 here. You can look here in the bottom left corner. M4 and M3. There's a simple circuit. Can you visualize it? Whether it is correct or not? You can check yourself. Then we are doing a circuit analysis here, and we will find the resistance R out one. This one R out two. Sorry, R out two, not R out one. We will find this R out two. Then we will proceed. Okay. So till now we have used a KCL at node x1, that is Ix plus GM3 VSG plus okay, is equivalent to Vx minus Vx is this Vx minus Vd4 by RD. This is a simple KVL. Then we use a potential because the Ix current is coming on in this node x1. It has to leave this node as well because there should be no violation of conservation of. Can you tell me what is the conservation law that follows here? Which conservation law is here? Uh,
Where, sir?
if this is a one node, this is another node. Current splits. Current comes I here. This is I1. This is I2.
KCL, no, sir.
I'm talking conservation. Which conservation principle? And
Law of
here,
conservation of charge, right?
yeah, conservation of charge, right? Charge can neither be destroyed nor created. So that's what it follows here. So Ix comes in toward this node and leaves from here as well. So now we have VD4 as Ix RDS4. Let me just substitute it in the equation.
Sir, this time your voice, a little bit of noise is getting added, sir, while you are speaking. That is due to air or I don't know.
One second. I think, so, anyone else facing issue? Am I clear? Anyone else is facing an issue?
Small, that is due to air, sir. I
Hmm?
think that is due to air, sir. While you are speaking, the noise, that air also getting added, so that your voice is somewhat distorting.
Okay. Should I speak slowly?
You should speak somewhat loudly, then it may not occur, sir.
Okay, okay. So we will just do the calculation here. That's a simple analysis. So this, if this is okay, then let me just substitute the values. So it will be Ix plus Gm. What is here? GM3, GM3 VSG, right? So here Vg is 0 and this potential is Vd4, right? So I can write Gm. This is simply, one second. This is simply GMVD4. Whenever you have any confusion, please just unmute yourself and let me know. This is VD4 equivalent to Vx by RDS3 minus VD4 by RDS3. Now we know VD4 is Ix times RDS4, and we will just do the simple substitution. This will be GM Ix RDS4 is equivalent to Vx RDS3 minus Ix RDS4 by RDS3. So transferring the variables, we will get, I'm taking Ix common directly. This will be R1 plus GM RDS4 plus RDS4 by RDS3 is equivalent to Vx by RDS3. Now we know R of 2 will be Vx by Ix, just multiply by RDS3 on both sides. It will be RDS3 plus RDS4 plus GM. What is this GM? This is GM3. This is GM3. So this will be GM3 RDS. Okay, RDS3 and RDS4. So this is the resistance we got by using this analysis. Okay. Now one thing is one approach. What we can do is we will just now take the circuit that is like this. A second. This is our circuit. Small signal as well will be grounded. This is my VN. This is NMOS. This is NMOS. And here is the output. And we will have the resistance of R output here. Okay, correct? So can you make a equivalent circuit? We don't need to, in this method, we will not calculate GM we can directly use the circuit and just add an R out here. And then we will do simple KCL and KVL to get an answer. Okay, and we draw the equivalent circuit. It will be simply like this. Yes. Please unmute yourself if you have anything to say.
Hello.
Hi, sir. Yeah,
Sir, can I have one question?
yeah, please.
Uh, in the transistor M4 on the topmost
One second, 1 second. Okay, M4, yes.
M4. Now you consider GM4 VHG as a zero, correct?
Yes, yes.
Why is it so? Because gate is grounded.
Gate is grounded and source is also grounded.
Okay, fine, fair enough, fair enough. And okay, fine,
Mm,
fantastic, sir. Thank you, thank you.
okay, okay. You just draw this equivalent circuit or directly I will just note here. For PMOS, this is source, this is ground, and this is its drain. Is this clear? So I will
Yeah,
just
yeah. Thanks a lot. Thank you.
note down the terminals for PMOS. So this is it. And now I'm drawing the equivalent circuit for the below portion. So it will be like this. RDS 2. This is, this is GM2 VGS. And this will be resistance R out 2. Okay, this is your V out. And similarly, we have here RDS2, GM1, VGS, and we have here VN. Okay, so here you cannot take GM2 VGS is equal to 0 because there is some potential S here. Similarly, this is GM1 VN. So now we have V out, we have V in. We just need to solve the circuit and we will get our V output by V in. Okay, so here if I take this as I out, my V out will be minus I out times R out 2, right? Just keep this as it is, right? Okay, now if I use a KCL here, it will be I out is equivalent to GM2 VGS. Just follow the steps and look at the circuit. You will understand these terms. This is V out. We are now using this current. What is the current flowing for RDS2? It's simply V out minus Vs by RDS2. Okay. So this is equivalent to I out. And here the current flowing will be I out again. So this I out will be equivalent to GM1 VGS plus Vs by RDS 1. Sorry, this is 1. Right? So this is I out is equivalent to GM1 VGS is V in plus Vs by RDS 1. So this is my equation number 2. This is my equation number 1. So I can see from equation number 1 Vg is 0. So from equation 1 can be rewritten as I output is equivalent to GM2 minus Vh because Vg is 0 plus V output by RDS2 minus Vs by RDS2. Now you can see these and I output again. You can write I output as V output by R output. So I output is minus times V output by R out. Now you can see these are the very cumbersome equations you have, but two variables. And to solve these, you have two equations now, and you have two variables. And V in V out, and but there is Vs as well. So we need to take care of Vs as well. Okay, we need to find the equation in V output and V input. So we need one equation. Like for example, if I take this equation, equation number 2 here, I write Vs in terms of I output and V in and substitute it in this equation. So I will get some equation in terms of V output and V input, right? So, but you took a lot of time in solving in this way. So you can solve now this, right? These are two equations. You just need to manipulate the terms. But what we will do is we will stop this type of solution here, and we will use another approach. So you understood this much, how you can solve this from this. You don't need me to solve this. If you want to, I can just solve this, and we can then compare the solutions. So you understood this, how you can achieve the answer by using this method. If you have any doubts or you want any more clarification about the steps, so I'll be pleased to repeat again. If no, we can directly move to the second approach. So it should mean that you are comfortable with the previous steps. So you understood all the steps. So the second approach is, do you remember what is the second approach? Calculate.
Minus GM into R out. GM into R out, sir. First, we need to find out transconductance and output resistance.
Okay, you calculate R out and you calculate short circuit GM, right? Correct? So let's first calculate R out. Let's go back to the circuit. So you look at the circuit here, you look at the circuit. How will you calculate R out? By this, right? And while calculating R out, what step you have to take? All the sources have to be grounded, right? So V in has to be grounded when we are calculating R out. R output 2 we calculated right in this step. So this is our R out 2. And similar way, we will calculate R out 1. Okay. So can you tell directly? Okay. So we just recently, in the previous session, I told you about this. I want you to answer this. So what will be our output here? What will be our output?
R out. Yes, sir.
What will be our out here in this circuit?
Yeah, source resistance is also present there, sir.
Yeah. Source resistance is present. So can you tell me what will be the R out?
R out. I mean, so it should be 1 plus GM into
GM into
RD
RD, right?
divided by. So I'm not getting exactly.
Mm-hmm. Okay. So let's quickly solve this flow. Let me just tell you, it is RS plus RD. It will be like this. So just for the repetition, we won't solve the previous circuit. But I will give an idea about this one. So that will make it easy to solve the rest part of the circuit. So if I just use this circuit and this is grounded, gate is grounded, and this is GM, VGS, this is RD. So this is at potential Vx. So what will be current here? Coming is Ix is equivalent to Vx minus Vs by, sorry, no, this is grounded, so it will be simply, so this will be Vx by Rd plus Gm Vgs, right? So it will be Ix times Vx by Rd minus GmVs. And Vs will be, what is Vs here? Current is GmVGS. GmVGS times Rs. Right? Correct? So this will be minus times GM RS. There is one step here. Need to consider one thing here. Let's forget RD in this case. RDS. This is IX. So this will be VX minus VS by RDS. I have shown this in previous session, right? Do you remember? Hmm. So this is IX simply here. This will make this simpler to solve. So Vs will be Ix times Rs. Yeah. So this is Vs is equal to Ix times Rs. Is this correct? This one? Yes, Vx minus and this will be minus Vx. Okay. So our aim is to calculate Ix by Vx by Ix. So just write it. Vx by Rd is minus Gm Vx is Ix Rs minus Ix by Rds. Transfer the variables. Ix is equivalent to 1 plus GMRS Rs by Rds is equivalent to Vx by Rds. So we can write it as Vx by Rs as Rds plus GMRS Rds plus Rs, right? So my R out for the circuit is your intrinsic resistance plus source resistance and gain GM Rds. This I told you in last session to remember. How you can remember is if you have normal, uh, if this is your normal circuit, total R out is looking here. What is total R out? Can you tell me directly? It's RD parallel RDS, right? Right? For the circuit, it is simply RD parallel RDS. Now, for the same circuit, for the same circuit, if I now connect an RS here, so it should be remembered in this way. For this circuit, R out is, let me just give a general definition here so you guys can remember it easily. General definition for output resistance. Keep in mind it's looking at the drain. Okay, so R out is, what is the total output resistance? Okay, this is output resistance. Okay, so there has to be one term that is output resistance plus some part of source resistance. Okay, so that part of source resistance is given by this resistance, this term. That is Rs. It's not directly Rs. It's Rs multiplied by 1 plus gain. Okay, is this understood? Can you remember the formula now? This is output resistance plus part of source resistance, and source resistance is, if it is RS, if RS is 0, then R out is simply RD. Here it should be, if I take, if there, for example, in the circuit there I didn't consider RD, so if there was RD, then it will be RDS parallel RD. Okay, let's keep it percent. We'll keep it as RDS. So if this is understood, we can now directly solve our previous question. Now, can you tell me? Okay, let me just. Uh, can you tell me how we will solve this now? R out 1, you can calculate R out 1. We will take M3 as our main transistor, and the resistance of M4 will be treated as source resistance. Okay, understood? And similarly, to, to calculate R out 1, we will treat M2 as our main transistor, and resistance of M1 will be treated as source resistance. Okay. Now I want you to tell me what will be R out 1 and R out 2. Let me just. Okay. One second. Let me just draw the circuits as well. This is M3, M4. This is R out 2, and this is M2, M1. This is R out 1. Okay. Tell me what will be R out 1? Okay, to make it easy for you, let's first see. Uh, this is we are looking from here, looking into this terminal. We are looking. This is drain. Okay, so we are looking into drain. So let's see first for this simple transistor, what will be. Let's say for simple transistor, it will be RDS3. This is here looking into drain material. So what will be here? This is grounded, so this will be 0. So its R out will be simply RDS3. Okay. Similarly, here if I look here, its resistance will be RDS1. Now, can you tell me what will be R out 2 and R out 1 directly?
Sir, RD2 is
Hmm.
RTS2, sir.
R out 2 is made of M3 and M4.
Okay, sir, sir. Sir, RDS3, sir. While you taking without considering source resistance.
So it will be no, no.
RDS3.
I'm just saying this for example. If you want to just check for a single transistor, so here main transistor is M3, right? And
Yes, sir.
this will be source degeneration.
Yes, sir.
So this will act as a M4 will act as a source resistance,
Yes, sir.
and M3 will act as your main transistor, and its resistance will be main resistance.
RDS3.
So this will be, so tell me the full answer. What will be R out 2?
RDS3 1 plus GM into RDS3 multiplication of RDS4, sir.
Multiplication of RDS4, correct? So anyone else can tell me what will be R out 1?
Sir,
Unmute the mic. Let's wait if anyone else can answer this. It should be easier now. So M2 is your main transistor, M1 is your source resistance. Here the source resistance is RDS1, and this has a resistance of RDS2. So what will be R out 1? Simple. Just look at R out 2, repeat it for these two.
RDS2 1 plus GM RDS2 multiplication of RDS1, sir.
Okay, this will be RDS2. This will be 1 plus. This will be GM3, right? So this will
Yes,
be
sir.
GM2. This will be RDS2 multiplied by RDS1. Okay, and now our total will be
Parallel of RO2 and
RR2 parallel RR1. So this we understood how to calculate the resistance. Now
transconductance.
next step is for this circuit to calculate. We calculated R out total.
Sir, sir, I'm getting one thing, sir. So we don't need to directly go to transconductance. Now, whenever input is applying, that the majority cases the transconductance will be GM1 only now.
No, but there are multiple transistors, right? So there will be uh, somewhere your voltage won't be directly. So in that only case when Vi directly goes to output, but here there are multiple transistors, right? So
Yes,
Vi directly won't apply. It won't be simply AV times Vi. AV where AV is GM. R out simple. Okay. So there will be
I know,
some.
sir.
Hmm?
I understand, sir. While we
Yes.
are in this case, we find out R out, no, sir. R
Yeah,
out through this
R
method.
R out we found. Now we will just directly find the GM effective.
Yes,
Okay.
sir. While finding GM, so
Hmm.
I get doubt, sir. We are applying input to V1 only, transistor one, right?
Yeah, yeah, yeah. You are because only you are applying a small signal for this transistor M1, so you have to consider this transistor only in calculating
Yes,
the
sir.
GM. Yes.
Yes, sir.
So it will be GM1 times something. Okay, so
Yes, sir.
that's something we have to find by using this method. All right.
Yes, sir.
So should we move forward?
Yes, sir. Yes, sir.
Okay, just give me a second. So in GM to find the GM effective, so what are the steps? V output, ground, right? So when I ground this V output, can you see that the above circuit need not to be considered in the analysis, right? Because V output is now grounded. So you only will consider M1 and M2, correct? So let me just take these two transistors only. Small signal analysis. So this will be grounded. V output is grounded. This is V in. This is grounded. Correct? This is our circuit. And let me just draw small signal circuit again. This will be GM2, VGS. This will be RDS2. This will be grounded. RDS1, GM1, VGS. And this is our VN. Okay, this is our VN. Can you pick up your pen and paper and find GM effective? I will give you 3 4 minutes to find GM effective. GM effective will be your, this is I out. Okay, GM effective will be I output by V in. I will give you 3 4 minutes to find yourself. Then, if you are not able to, then I will try. If anyone has any questions, if you are not able to say by turning on your mic, you can anytime post your questions or queries in chat box. You need not to be afraid of anything. I'm a student like you guys. So it will help you with your confidence as well if you are able to question about the things you take. So feel free to ask anything if you want.
Sir, GM1, sir. My approach is, sir,
Mm-hmm.
should I explain, sir?
Yeah, yeah.
Yes, sir. While you are connecting GM1, VGS, RDS1 upper, make it as a node. Whatever out is coming, it should enter while it is dividing. But while at this node, it should add now.
So what is the first step you did? You made this equivalent circuit like I have.
Yes, sir. Same thing.
Okay.
GMVG, what and all current we are getting, it should be added at this GMVGS RDS1. It should added no, sir. At this node upper.
So the I out is coming from the upper node, and it will come here as well. Here
Yes, sir.
this is I out is.
Yes, sir. Yes, sir. Exactly.
So what you are saying is I output is equivalent to GM1 VGS plus Let's call it as VD1 plus VD1 by RDS1, right?
Yes, sir.
This is what you're saying. So this will be GM1 VGS is
PL.
simply V
Yes.
in plus VD1 by RDS1. So this is what you say, right?
Yes, sir.
So now, after that,
After that, we need we need to find out the VD1, sir.
we need to find out VD1. And how do you do that?
VD1.
You can go to this node. Let's say this is the X node. At X, I out is GM2 VGS plus 0
VX by
minus VD1
VG.
by
Yes, sir.
RDS2, right?
Yes,
And
sir.
GM2 VGS is minus GM2 VD1 minus VD1 by RDS2. So now you have I out in terms of VD1. Okay. Run like a pages. So this is okay.
Yes,
I
sir.
output is minus if I take VD1 as common, so this will be GM2 plus 1 by RDS2, right? So
Yes,
now
sir.
you have VD1. Let's write it in the simplified way. This will be 1 plus GM2 RDS2 divided by RDS2. So VD1 is RDS2 divided by 1 plus GM2 RDS2 I out. Correct? So
Yes,
now
sir.
going back to this equation 1, this is equation 2. Now going back to this equation 1, we have I output is equivalent to GMV in GM1 V in, right? It should be GM1, yes, it is GM1 plus VD1, that is RDS2 by 1 plus GM2 RDS2 I out. Okay, so I will take I out on the left, so it will be 1 plus RDS2 divided by 1
Understood.
plus GM2 RDS2 is equivalent to GM1
GM1.
V in. Now what I said in the first slide is GM effective is I output by V in. So GM effective is I output by V in. So now you can see here I output by V in, that is GM1 multiplied by 1 plus GM2 RDS2 divided by 1 plus GM2. I have skipped one step. You can just follow it. 1 plus GM2. I multiplied it here, right? I have multiplied it here. Plus there is some mistake here. There is a mistake here. There is a mistake here. 1 second. I out some mistake here. 1 second. So I out is GF1 V in plus VD1 by RDS1, right?
Your screen is not getting moves. It is stuck or what?
1 second, 1 second. I was just checking it. I think there is one second. Let's check again whether we have written it correctly or not. I output here at node VD1, as you said, is GM1 VGS, right? And plus it's VD1 by RDS1, correct? So it will be GM1 V in plus VD1 by RDS1. So equation 1 is correct, no doubt about it. And then we go to equation this node X. So I output is GM2 VGS plus 0 minus VD1 by RDS2, right? Which is minus GM2 VD1 minus VD1 by, okay, RDS2. This is fine. Okay. So I output here, yes, this VD1 is also correct. We have done some mistakes over here. Mhm. So VD1 is RDS2. There is some constant multiply current, so it is a voltage, unit is voltage. Right. Yes, here. So I was telling there is a mistake here. So why did I tell you that there is a mistake? Can you just tell me why? Can you look here in this equation?
Yes.
So you can just see here 1 plus GM RDS. GM is 1 by ohm, RDS is ohm. Ohm by ohm will cancel. This will be unitless in denominator, right? And you can see in numerator you have RDS2 that has a unit of ohm, but it has a 1 here, unitless quantity. So you cannot add a unitless quantity to the quantity which has some units. So that's why I found out that something was wrong with the equation, right? So what we had did, we forgot this RDS1. So there was a RDS1 here, right? So now this RDS1 has unit ohm, RDS2 has unit ohm, ohm and ohm will cancel. Similarly, 1 plus GM to RDS has a unitless quantity, so this remains a unitless quantity.
Yes,
Correct
sir.
now?
Yes. Correct. Correct.
Understood?
Correct. Yes.
This is RDS1 here. So, so you need to if you want to check your derivations, this is a very best way to check uh, units. Units is the best way to check whether your derivation is correct or not.
Yes, sir.
Okay, so this is RDS2. So if I divide both sides by numerator and denominator by 1 plus GM to RD, so I will get GM1 multiplied by RDS1 divided by RDS1 plus RDS2 divided by 1 plus GM2 RDS2. Alright, so this is your effective GM. Now your gain will be simply this GM effective multiplied by R of total. So now just check one thing is here in this question what we asked to calculate the output or input, but there are some filters, GM1, B1, GMB3, B3, right? So what you can do is, once you derive these four derivations by using the simple formulations, you just need to do one thing, that is, instead of G1, GM1, instead of if, let me just note here, if GMB values are also given, just add them. Like here, example here, it was GM1, so you need to write GM1 plus GMB1, okay, instead of G. Just that, okay? That will give you the correct answer. Alright, similarly in R out, you have GM3 here. This will be GM3 plus GMB3. Similarly here, it will be GM2 plus GMB2. Okay? So I hope you will remember these formulas, how you can derive these formulas. Just keep this into mind and you will be able to solve any question I think. So any questions or any confusion till now? Just and then forward. In the next question, we will just use the same analysis again directly. And this was the last time you asked about this question. We will just quickly use the same method. Hmm, we will try to get an answer. Have you tried yourself?
Yes, sir. Could you please tell it? I will try, sir.
Let's use the GM multiply by R out method. Okay. So you have two sides. You have to calculate this is R out one, this is R out two, right? Tell me what is R out one? It should be simple now. It
Yes, sir.
is RDS three
1 plus RDS3, 1
plus
plus GM3 RDS3 into RDS4.
right? Similarly, what is R out two?
Sorry, here R out to,
Let me just first write, then I will ask you guys why. Tell me, is it correct?
yes, sir, correct.
Right? Because when you see here from this node, you will see you
That
are looking here. This is drain. So this has a resistance of RDS1, right? This is a resistance of RDS1, and this is in parallel to R. So that's why I have written a source resistance of R parallel to RDS1. Correct? Once you remember this formula, these circuits will be very easy for you to solve. So if this is okay, then what we need to do is calculate R total, that is R out 1 parallel to R out 2. Okay, next, what is the next? Next is short circuit GM. So when I use the short circuit GM, I will just attach a ground to V out, and I will be left with following circuit. Correct? Let's try to solve this. This is okay, right? If this is okay, then just let me just draw the circuit, equivalent circuit. Okay, so this is I out. Let me just quickly write what is I out. I out is here at this node, node X. Now for 2021. GMA is also. You can see that VD1 is VS, so I could have directly written VS. Okay, so just directly write something because it is again a repetitive analysis. So this is now easy for you, I hope. Just quickly write it here. Okay, but because we have done it a lot of times, so I will just directly write GM now. GM is I output where we in, so it will be this GM1 DS1. If you have any, you solve it at your end also. I hope you will get the same answer. This is your final answer for GM. Okay, so we should the values in your numericals and you should get the answer. Now you know how to calculate GM now, you know how to calculate auto, then gain is simply a GM multiplied by GM multiplied by R. Any questions till now? Because now we will move to a different topic. Hmm. If you have any doubts or anything till now, you can ask before we move to questions like these. Do you have any questions? We will discuss something related to current mirrors now. Have you gone through the lectures of the current mirrors? Or what is
Yes,
current
sir.
mirror? So what is current
Yes,
mirror?
sir. Sir, whenever two transistors are in parallel, one of the transistor gate and drain are short circuited. If
Hmm.
they are maintained with the same gate voltage, uh, ignoring the mismatches, the same second transistor also getting the same current, then then the is
Okay, so yes, you're right. So before we go to current mirrors, which is the topic, let's see why current sources are used. Okay, so if someone says to why you use the current source in the circuit for the biasing, so how does it help? Okay, so uh, let's see what are the benefits of using a current source? Okay, so if you have a transistor working in saturation, can you tell me what is the formula for IDS? This is drain, this is source, this is the
1 by 2 mu n Cox W by L VGS minus VT whole square.
noise. That is VGS minus VT whole square. And what will be GM?
Ignoring the channel information.
What will be GM?
Yeah, mu n Cox W by L VGS minus VT.
Right? So your GM directly depends on VT, right?
Yes, sir.
Okay, let's suppose now there are some factors like temperature, stress, or anything, any uh, external body, or due to potential differences or stress, you keep your device in stress. There is a change in VT. Let's suppose initially it was VT naught, now your VT is VT naught plus delta T. Okay, sorry, not delta T, delta V.
Because of temperature difference, sir.
Let's say the temperature is one of the factors. Uh, let's say this is delta VT. Okay, so let's say
No,
that due
sir.
to due to
Because
change
of
in
substrate doping, sir.
okay, that's what I'm saying. There can be multiple factors. Let's for the level you are at right now. Let's say due to temperature fluctuations, there is a change in threshold voltage. Okay, this you understand. Now let's know denote that change as delta VT. Okay. Now can you tell me what will be GM new? GM new will be mu n C ox
Less, sir. Yes, sir.
W by L VGS minus VT naught plus delta VT.
It will
Right?
reduce the transconductance.
Is okay.
Yes, sir.
So I can write GM new as mu n C ox W by L VGS, right?
Yes, sir.
Minus VT naught plus, sorry, not plus, minus mu n C ox W by L delta VT. Is it correct?
Yes, sir.
So if I denote this as GM naught, so is this my GM naught?
Yes, sir.
Right? So my GM new will be equivalent to GM naught minus mu n C ox W by L delta VT. Right? So
Yes, sir.
if I just take it on the left hand side, GM new minus GM naught will be delta GM. This will be equivalent to mu n C ox W by L delta VT. Now divide both sides by GM naught. So this will give me a relative change in GM. This will be minus P of W by L delta VT divided by GM naught. And GM naught, it is mu and C of W by L VGS minus VT naught. So mu and C of W by L will cancel. What will remain is delta VT divided by VGS minus VT naught. Okay. So delta GM by GM naught is a significant value of delta VT by VGS minus VT naught. So there is some change in if there is some change in threshold voltage, there will be a significant change in GM as well, right? You can see from this equation. Similarly, there can be a change in mu. What is mu?
Mobility.
Mobility, right? So mu nu can be mu naught plus delta mu. So what if it is happening in the circuit? So my GM nu will be mu naught plus delta mu C ox W by L. Let's say at this time Vt it is constant, so I will just treat it as Vt. So we will see only change with respect to mu naught. So this will be GM nu will be mu naught C ox W by L VGS minus VT plus delta mu C ox W by L VGS minus VT. So once you do the same steps, because this will be again, let's say this is GM naught, so this will be delta GM, GM nu minus GM naught will be delta GM, so this will be delta mu, oh sorry, this is C ox, C ox W by L VGS minus VT. Divide both sides by GM naught, you will get delta GM by GM naught is equivalent to delta mu by mu. Okay, so this is what you will get. So this has a significant dependence on change in the mobility. Now, this is when we used a voltage source. Okay, so you are using here VGS for biasing. Now, if current source is used for biasing, okay, so just tell me the formula for GM in terms of current source.
Square root of 2 I naught.
So that will be in terms of I, it is square root of 2 mu W by L. One second. IDS, right? Cox, I forgot Cox. Now, here IDS is used as used to bias the circuit. Now, if IDS is constant, because at that in this case the VGS was constant, in this case the IDS is constant because IDS is used to bias the circuit. So there is no change in VT. No, even though there is change, even though there is some change in VT, there is no VT term in this equation, right? So delta GM by GM naught is 0 for VT change. Can you see that if we use a current source, our circuit is less sensitive, not less sensitive, it's not sensitive to threshold voltage fluctuations. Understood?
Yes, sir. That is the reason why we are not using the voltage biasing now, sir.
Yeah, that also will depend on several things, but whether you want mostly current biasing is used in if you want a current amplification or you want some, let's say, you want less variation in your currents due to the fluctuations of mobility and threshold voltage. And also if you want more current to flow in one branch or less current to flow in other branch, so that's when you use the circuit biasing. For these cases when where you don't want the threshold voltage fluctuation in all. In these cases, the current biasing is a preferred version. Okay, so so if it is understood, can you tell me what will be delta GM by GM naught if there is a change in mobility?
Could you repeat again, sir?
Yeah, if now GM is if mu change from mu naught to delta mu, so GM will be 2 mu naught plus delta mu C ox W by L ID, right?
Yes, sir.
So can you tell me what will be delta GM by GM naught? So can I write it as here 2 mu naught C ox W by L 1 plus delta mu by mu naught?
Yes, sir.
So it will be GM nu will be 2 mu naught C ox W by L IDS multiplied by 1 plus delta mu by mu whole is power by 2. Okay, so if we assume delta mu by mu naught is not that large, we can use a binomial form and we can directly write gm nu as this is your gm naught, right? This is gm naught. This will be 1 plus delta mu by 2 mu naught, right? Using the binomial term for this term. So this will be gm nu minus gm naught is equivalent to delta mu by 2 mu naught. Dividing both sides by gm naught. So what I will get is delta gm by gm naught second. I don't need to divide it by divided by. So this is gm naught, gm nu minus gm naught is equivalent to gm naught delta mu by 2 mu naught. So this will be, if I divide it by, this will be delta gm by gm naught is equivalent to delta mu by 2 mu naught. So can you see here, in previous case, it was delta mu by mu, and in this case, it is delta mu by 2 mu naught. So there is a 50% reduction in sensitivity, right? 1 by 2.
Yes, sir.
So current sources are make a circuit less sensitive to the change in mobility and threshold voltage. Okay. So now the question is how current sources bias the circuit. Now I will give you a transistor and this is my current source. Let's say I know. How does it bias the circuit? How does it turn on the device?
Sir, it depends on the gate to source voltage, sir.
So you're not applying voltage here in current biasing. That's what we uh,
Oh, yes, sir.
summarized from the previous discussion. So we are using only the current source here.
Yes, sir. Yes, sir. But the drain current should, it is a drain current, no, sir. Drain current will have, it will have some current, and the rest of the parameters will have VTH.
So
With this,
drain
we'll
current,
find out
let's say this is drain current. Drain current,
1 by 2 mu n C ox VGS minus VT whole square.
drain current will only flow if VGS is greater than VT, right? So
Yes, sir.
this is my gate, this is my source, this is VGS. So how does this VGS change? Do you know? How does this VGS appear?
Uh, mean means mean it is a input input no sir.
You don't in circuits where you apply current source to bias a circuit, you don't apply voltage here.
Okay, okay, yeah, I get the point, sir. Because of the infinite resistance.
Okay, you here connect. Yeah, this is like this connected.
Yes, sir.
Okay. Now, can you tell me how does the voltage get generated in from gate to source?
It is a VDS. VDS is equal to VGS, sir. It is a short direct connector, no?
Okay, so let me just see how what happens. Let's start. At t is equal to 0, do you agree that without any connections, ID is 0? Okay, so there are no
Yes, sir.
connections. You have not applied anything. ID will be 0, right?
Yes, sir.
Okay. Now if I now at t 0 plus connect I naught. I naught is a current source. Okay. So what happens is there is a capacitor here. All the devices have a parasitic capacitance. Let's call it as CP. So what happens is, since this is MOSFET, we assume that this current is zero. So what happens? ID is zero. Okay. So wire and DC. For the DC case, from t is equal to zero, the capacitor will conduct, right? So you know that if this is the V output of capacitor and
Yeah.
this is V
Capacitor will
input
be short circuited, no, sir.
at the initial case when there is no charge developing. So after applying this potential, this current here, and ID is zero. So what happens is this current goes in this direction. Okay, and due to this current, there starts a charge pile up in this capacitor. Okay, and due to this charging of the capacitor, there gets a potential developed here. Let's call it as VCP. Okay. So what happens is at zero, ID is zero, and you apply a current source of I naught, the whole current will go to the capacitor and it will start charging the capacitor, and charging the capacitor will increase the potential. It will increase this potential and which subsequently increase the gate potential. Okay. So as let's call it IC. IC ID 0 IC is equivalent to ID VCP increases. Okay, 1 second. Do you understand? This is important for the current mirrors and current biasing. So once this reaches, once this, 1 second. If this is understood now, this VCP increases means your VGS is also increasing, right? You can see from this figure, VCP is connected directly to the gate, and since the transistor is not conducting, so whole current flows through the capacitor. Capacitor goes on charging, and it increases the potential. This potential in turn increases the VGS. When VGS reaches VT, transistor turns on, right? When the transistor turns on, ID increases. So ID will increase till ID is equivalent to I naught. Is this understood? Since when ID is equivalent to I naught, that
Yes,
means
sir.
whole current I naught is flowing through the transistor and it's not flowing through. And at this time, IC is 0. That means capacitor is fully blocking state. Alright. So when ID is I naught, your whole current from the current source is flowing through the transistor, and at that time VCP is such that no current flows through the capacitor. Alright, so this is how current biasing is done. Then same we will take this step into the current mirror part. How does it how does so this is if this is understood, let's give a brief example of current mirror. 1 second, give me 1 second. Let's say now I have this. Okay, let's say this is a here I reference is a reference current source that is connected. All right. So tell me if this is WP, this is WP, this is WN, this is WN. So what happens in the circuit due to this IF? If a total IF is flowing, there will be some potential here, right? This is the PMOS and current flowing through. This is in saturation, right? The current flowing through IR and this is IRF. This will develop some potential here. Okay, this will develop some potential here, and this will develop some potential here, and this will develop some potential here. Let's say this is VGS 1, and this has VGS 2. Now tell me if two these two are identical, and you know the formula, right? So if these two are identical, 1 and 2, that means mu n is same, Cox is same, W by L is same, Vt will be same. So if you want same current to flow through this transistor, what should be same? VGS, right? VGS should be same. So that is what is the principle of current mirrors. What happens is the potential developed here, in this case, VGS1, that directly gets applied to this VGS1, VGS2 as well. That is VGS2 is directly equivalent to VGS1. So let's assume that there is no CLM, absence, absence of CLM, so that there will be no drain dependency on the current. Let's assume that device are in saturation and no CLM. That means that the same current of, since you know that if you connect two transistors in series, same current should flow. Similarly, here I reference will flow. Okay. So tell me what is the potential here? What will be the VSG? It will be simply what is here VSG. Okay. Understood? This is a one example. Let's apply it here in this question. and we will stop after this, and we can continue in the next section for the current mirrors. Tell me, there will be some potential here. Okay, let me write it IAW1 current. It will be mu n C ox AW by 1 W1L VGS minus VT whole square. Okay, now this same VG will get applied to transistor with BW1. So let me call it as I1, let me call it as I2. So my I2 will be, let me call it I1. My I2 will be mu n Cox BW1 by L VGS VGS minus VT whole square. Now this current is equivalent to I reference, right? Because same current should flow in the series. So if this is equivalent to I reference, that means if I okay, so that means I will just write here mu n Cox W by L VGS minus VT whole square will be equivalent to I reference by A. I hope this is understood. Just divided I reference by this A term to get this term. So because this term is common in this equation as well, so I can write I2 as B times mu n Cox W1 by L VGS minus VT square is I reference by A. This is understood, right? Let me just write it clearly. This is I reference multiplied by B by A. But that is not the goal. Goal is to calculate I copy. I copy is flowing through this branch. So what is the next step? If I2 is I reference multiplied by B by A, so that means this should flow through here as well for CW2. So this will be, so I can write for CW2 as well, I2 is mu n Cox, sorry, mu P Cox CW2 by L VSG minus VT whole square. And I2, you know, it is I reference times B by A, and I can write it equivalent to mu n Cox W2L, let me just call it overdrive, V overdrive whole square, multiply by C. If I divide by C, what I will get? For this case, for transistor C2, mu P Cox W2L VSG minus VT whole square will be equivalent to I reference times B by A times C. Now, what will be I copy? I copy will be simply mu P Cox dW2 by L VSG minus VT whole square. Okay. So can you tell me finally what will be I copy? You can see here mu P Cox W2 by L VSG minus VT square is I ref B by AC, and I just need to multiply it by, you can see here the same terms here. So this will be simply I ref multiply by B by A multiply by D by C. Okay. Just a quick note, if you want to directly see what will be the current flowing given that all the transistors are identical, you can see I reference, if the current of I reference is flowing here, so the current flowing here will be simply the current flowing here multiply by what is the ratio of the W by L. Here it is B by A. L is safe, only width is changing, so it will be here the current will be flowing here I reference times B by A. Okay, so this is equivalent to this current C times W by 2. So here I copy will be whatever current is flowing through this branch, that is I2. I copy will be D by C of I2. I copy will be D by C of I2 simply. And I2 you know is I ref B by A. You can directly write I copy is ratios. Last initial. First is I ref multiply. What is the second one? B multiply its ratio A, then multiply D. What is it? What is the ratio? C. You can directly write it like this as well. We will take current mirrors again, and we will do the questions on the current mirrors again in the next session. So if you have any questions till now, you can ask. We have gone through the session. We had and we again did the questions on how to calculate R out gain and use the same method. We had some introduction to the current sources and why current sources and their analysis. So if you have any questions now, you can just ask. Then we can continue in the next session. So anything?
Perfect, sir.
Hmm?
No, sir, no, sir. Fine.
So
Everything is fine.
so we will take current mirrors again in the next session. So till
Yes,
then,
sir.
to do the questions and try to use the method. Try to remember the formulas. That will make it easy for you guys to solve the questions. Okay.
No, sir.
Okay. So let's see you. Let me see you next week then. If not anything, then I will just end the meeting.
Good night, sir.
Good.